Hello, welcome to Unit 7, Lesson 8, the Amazing Inverse Trig Function Race. Ready, set, go, solutions. So it says plot each number in the rectangular complex plane. So the rectangular complex plane basically just says that your vertical axis represents the imaginary number and your horizontal axis represents the real number. So our real part is 7. So 1, 2, 3, 4, 5, 6, 7, and up 5. 1, 2, 3, 4, 5. So 7, 5. I'll make the 7 nice and big. 7 and 5. There we go. Question 2. Same thing. Our real part is -4. So 1, 2, 3, 4. So -4. And our imaginary part, I'm going to actually put that above, -4. Our imaginary part is -1, so we're down 1. And we have our point right there. Okay, question 3 is -6i. So this is our imaginary part. And 2 is our real part. So 1, 2 as the real part. And -6, so 1, 2, 3, 4, 5, 6. -6 as our imaginary part. So there is our point right there. Question 4. So our real part is 8. So let's count over 1, 2, 3, 4, 5, 6, 7, 8. Okay. And our imaginary part is -6. So 1, 2, 3, 4, 5, 6. -6 down. So there is our point. Question 5 says, use the Pythagorean theorem to find the modulus of each number in problems 1 through 4. Recall that the modulus is the distance between the point 0, 0 and the point representing the number. So you could do the whole distance formula, right? I'm going to write that out first. I'm not going to do that for each one because there's no need to actually use it. But remember, the distance formula says the square root of the difference of our x values, or our inputs, I should say. So I'll call it x1 minus, since we're always using 0, 0, I'll say 0 squared plus y2 minus 0 squared. Now for us, since we're using 0 for our problems, this is really just going to come out to the real part squared plus our imaginary part squared, all under the square root. Very similar to Pythagorean theorem, right? Use Pythagorean theorem to find. So Pythagorean theorem, right, is a squared plus b squared equals c squared. Well, it's saying basically if we go ahead and take the square root of that c, we get the distance. So this is our distance. I shouldn't do it in blue. That makes it look like the square root is the distance. But this value right here is the distance. Notice I don't need to include the I, because the I just tells me what is the imaginary part, right? So we use B for that a lot. So for part A, I'm going to do the square root of 7 squared plus 5 squared. Well, that gives me 49 plus 25, or the square root of 74. Okay, here we can do -4 squared plus -1 squared. So we get 16 plus 1, or the square root of 17. Part C, so -6 squared, the order doesn't matter. -6 squared plus 2 squared. If I wanted to put the real part first, I would just swap those. So we get 36 plus 4, which is the square root of 40. And I can break that down into 4 times 10, because 4 is a perfect square. So the square root of 4 is 2, and I'm left with 10 still in the square root symbol. Okay, and here we have 8 squared plus -6 squared. So we get 64 plus 36, which is 100. And the square root of 100 is 10. Okay, question 6. It says multiply each complex number in problems 1 through 4 by the conjugate. So we're using those same problems above. Remember, conjugate, we create a difference of squares. And that's going to be addressed a little bit when it says compare our answers. A difference of squares. That way, the middle terms fall away, and we can end up squaring the imaginary part. So the conjugate of 7 plus 5i is 7 minus 5i. And I could have actually done 5i minus 7. It wouldn't have made a difference. So we get 49. I'll do the whole thing out, actually. Let's for the first one, I'll really show where we're getting this. So 7 times 7 is 49. And then 7 times minus 5i is negative 35i. And then here, positive 5i times positive 7 is positive 35i. And then positive 5 times negative 5 is negative 25. And then I times I is I squared. So these terms add to 0. So with 49 minus 25 I squared. And remember, I squared is equal to negative 1. So this becomes 49 plus 25. So we end up with 74. Okay. Part B. So for part B, I won't show as many steps here. So let's change that imaginary part to a real part. And remember, when I do this, when I say a plus b, and it's quite literally a plus b works really well because that's what we use for imaginary part. In real part, we end up with a squared minus b squared. So I'm going to use that shortcut. So negative 4 squared becomes positive 16 minus, well, I squared is I squared. Well, remember, I squared is equivalent to negative 1. So minus negative 1 or plus 1. So we get 17. Okay, negative 6i. I'm going to actually write this as 2 minus 6i. So my real part is first. So then 2 plus 6i. So I'm going to get 4 minus 36i squared, which becomes 4 plus 36, which is 40. Okay. Our next one. And if I had done that in the opposite order, I still would have gotten 40. So if I multiplied 4 minus 6i by its conjugate, sorry, not 4, 8 minus 6i, then I get 8 plus 6i, which gives me 64 minus 36i squared. Well, that gives me 64 plus 36, which gives me 100. So part E says, compare your answer to the ones you got in problem 5. What do you notice? Notice in problem 5, we have the square roots of these numbers. The square root of 74, the square root of 17, the square root of 40 before I simplified it, and the square root of 100 before we simplified it to 10. So compare your answers to problem 5. So in problem 5, we had these results under the square root. I'll actually write the word square root. Square root. So, our answers to problem 6 are the square of the modules. Moduli, maybe, the square of the moduluses of, let's say, each. And we avoid using plural. Okay, so that's a little comparison. Our set questions. Use the given information to find the angle between 0 and 2 pi. Round answers to the thousandth decimal place. So between 0 and 2 pi, it wants us working in radians, right? So that's giving us our answer in radians. So make sure your calculator mode is in radians. So to find cosine, to find theta, when we have cosine of theta, we want to take inverse cosine of this 0.9848. Now there's two places that cosine is positive, right? Quadrant 1 and quadrant 2. Quadrant 4. But since it tells us that sine of theta is greater than 0, this is the one we want. We want quadrant 1. So quadrant 1. So we won't have to change our answer that our calculator gives us, which is nice. So theta, if we do inverse cosine, theta, and it says, what, 3 decimal places? Yeah, so theta equals about 0.1745. So I'm going to round that up to 5. All right, question 8. So theta equals cosine inverse of 0.9848. Well, we already know that that is going to give us about, because that's the same number as before, so that's going to give us 0.175. But note here, this time we actually want to be in quadrant 4. So let me do that underneath, actually. So here we want to be quadrant 4. So let's sort of draw this out. So what we just got was this angle right here. We got theta is about 0.175. So what we want to find is this angle right here. So that's what we want. We want this theta right there. So if we know that the whole circle, that this is 2 pi, so what we're going to do is do 2 pi minus 0.175, because that's how far below 2 pi we are. And I'm going to make sure I just keep that number in my calculator so that it's as exact as possible. So if I add 2 pi to negative 0.175, I get, let's do it in my calculator to be exact, I get theta is about 6.109. Okay, now question 9. Question 9 says, explain why the answers to problem 7 and 8 are different, even though the calculator gives you the same answers for both problems. It says, include information about the meaning of the inverse trig function in the quadrant in which the terminal ray resides. So, let's talk about cosine. So cosine, let's see, let's draw a little. Let's talk about the quadrant. So when we do cosine of our angle, so in quadrant 1, it's positive cosine. And in quadrant 2, it's negative cosine. Well, quadrant 4 is also positive cosine. In quadrant 3 is also negative cosine. Oops, negative cosine. So our calculator doesn't give us all 4 of these. It doesn't know which one we actually are referring to when we're just putting limited information into our calculator. So it'll always give you, for a positive answer, if you do inverse, so if you do theta equals cosine inverse of a negative, it will always spit out something in quadrant 1. Sorry, of a positive. I don't know why I wrote negative. of something positive, it'll always give you something in quadrant 1. But if we put if we do theta equals cosine inverse of a negative number, it will always give us an angle in quadrant 2. So our calculator, calc does not give angles in quadrants 3 or quadrants 4. So if I kind of put those together, let's kind of put those together. So we said if we have a positive value, it's going to be quadrant 1. And if we have a negative value, it's going to be quad 2. Now I'm going to be more specific. The highest angle in quadrant 2 is pi. I'm actually going to flip these, quadrant 1, quadrant 2. So the lowest angle in quadrant 1 is 0. So it's always going to give us something 0 or greater. And then the highest angle is quadrant 2. So our answers will always be between our answers for cosine inverse. So when using theta equals cosine inverse of some value will be between 0 and pi, right? That's because that covers the positive and negatives. So we need to realize if it's actually in quadrant 3 or quadrant 4, how do we use our knowledge of a full circle in the coordinate system to get those answers? So that's our responsibility to do. That's not going to be something the calculator gives us. Okay, let's go to problem 10. So problem 10 says sine of theta equals negative 0.1908, and it tells us that tan inverse is less than 0. So let's first think of what our calculator gives us when we do sine inverse of negative 0.1908. And I'm going to do problems 10 and 11 at the same time, because notice once again we're using the same sine value. I'll put a 0 in there, 0.1908. And we're still in radians, the same directions apply. So let's pull out our calculators and do sine inverse. So inverse sine of negative 0.1908. And that's going to give us a value of about negative 0.19, and it said 3 decimal places, right? Am I remembering that correctly? 3 decimal places, yes. So 1919, so I'm going to round that up to 2. So that's what we get as an approximate for both. But remember, we're probably not going to have the same answer for both. We're probably going to have to edit one of these. So let's look at this part. Tan of theta, one is less than 0 and the other is greater than 0. So let's start with where sine is negative. So sine is negative in quadrants 3, in quadrants 4. So negative sine. So both of those are possible answers. However, it gave us, so since it, oh, no, there you go, negative point, it gave us this angle right here. This angle is negative 0.192. And for this one, for this quadrant, tangent of theta is in fact negative. So tangent of theta is less than 0. So that's our answer for question 10. Our answer for question 10 is just negative 0.192. However, remember our answers need to be between 0 and 2 pi. So if I just add 2 pi to this, I'm going to get my correct answer, because that's like adding a full circle. So let's go ahead and take that number and add 2 pi to it. So that number plus 2 pi, and I'm doing my calculator so that my decimals are exact as possible. I get about 6.0912, so I'm going to keep it at 1. So 6.091. So that's the angle there in quadrant 4. So this would be quad 4. Right. Now, where tan is positive, that's question 11. So tan, here we want a positive tangent. So tangent in quadrant 3, tan of theta is positive in quadrant 3 because it's a negative y over negative x. So those two negatives reduce out and become a positive. So this angle right here, our calculator told us is negative 0.192. Well, we can actually use the positive version of that number. So theta equals 0.192. And if we know this is pi, so this is going to be pi plus 0.192 because we're that much further. So what we really want to think is theta equals pi plus 0.192. So let's go ahead and do that in our calculators. Okay. I'm just turning on my calculator here. I know you can't see that on your screen. So we have 0.192 plus pi, and that gives us roughly 3.3335, so I'm going to round it up to 4. Okay, so now let's talk about question 12. It says, explain the answers in problems 10 and 11. Explain why the answers are different, even though the calculator gives the same answer for both problems. Include information on the meaning of inverse trig function in the quadrant which the terminal ray resides in. So we're going to do something similar we did before, but this time we're working with sine. So when we're talking about sine, let's do a big grid. Again, in here, let's say, so here sine is positive, and so is sine positive in quadrant 2. So sine is positive, but here in quadrant 3, sine is negative, and sine is negative in quadrant 4, right? We're talking about negative y and positive y. So sine is negative in the same places that y is negative. So our calculator always wants to give us a negative and a positive version of our answer. So when we're doing our calculator, it's going to give us quadrant 1 if we do sine inverse of some positive value. It's going to spit out an angle in quadrant 1 because that's the closest to 0 while still remaining positive. It wants to give us a smaller number. It wants to give us numbers closest to 0 while having a positive angle. So there's no need for it to give us something that's bigger than pi, right? So if it's negative though, this is too far. That's going all the way there. We have to go over to the third quadrant versus just going downward. So if we have theta of equals sine inverse of a negative number, it's going to give us an angle in quad 4, and it will give us a negative angle. Angle measure. Because it wants to give us the number closest to 0. So it's not going to give us a number like 5 or 6 radians. It's going to give us a number like -1 radians or negative point something radians, right? It wants to give us something as close to 0 as possible. So when we're thinking about our possibilities for theta, well, the biggest possibility is that it's all the way up here at pi over 2. That's the highest number it needs to get positive. But here, instead of thinking of this as 3 pi over 2, we can think of it as negative pi over 2. So it can give us something as low as negative pi over 2. So that's going to give us sort of the positive values and the positive sign values, I should say, positive sign values, and the negative sign value. So our calculator will always give it that. So our calculator, so calc won't give us an angle in quadrant 2 or quadrant 3. It doesn't need to, because it's going to give us one answer, so it's going to give us the closest answer to 0, whether or not that's positive or negative, right? So it gives us the closest answer, to 0 radians, whether it's positive or negative. Or negative. Now that wasn't an issue with cosine, because for cosine, the positive and negatives were in quadrants 1 and 2. And so it didn't matter, like if we flip back up to cosine really quickly, where did we do that one? Right here. So this distance is just as far as this distance. Those are both negative. So in this case, if the distances are equally as far from 0, our calculator is going to give us the positive value. But in this case, this distance is further from that distance from 0, so it's going to give us the negative values, because that's how we keep the number closer to 0. That's how the calculator keeps it closer to 0. Okay, so question 13 and 14. Again, let's do these together, since we see the exact same value there. So theta equals tan inverse of negative 0.4663. And it's going to be the same thing down here of negative 0.4663. So let's pull out our calculators and see what this gives us. Okay, so inverse tangent of negative 0.4663 gives us an angle of negative 0.4363. So I'll stop at negative 0.436, 3 decimal places. So now, let's look at where tan is. Let's change this to black, I guess. Let's look at where tan is negative. So tangent is negative in quadrants 2, where x is negative but y is positive. So tan of theta is negative. In quadrants 4, tan of theta is negative. So we know tan of theta is negative in those two quadrants. So now let's look at this. So where's sine of theta? Positive. So sine of theta is positive in this quadrant 3. So this, we want an answer that falls, sorry, I said quadrant 3, in quadrant 2. And here we switched it to cosine. So where's cosine positive? Well, cosine is positive in quadrants 1 and 4, but we're not dealing with quadrant 1. We're only dealing with quadrants 2 and 4. So this is going to be quadrant 4. So quadrant 4. So let's analyze what it gave us. It gave us negative 0.436. So negative means we're going clockwise, right? So negative means we're going to go downward. I'll change this to pink. So this is the angle here that it gave us. Theta equals negative 0.436. So remember, this whole thing is 2 pi. So if I want this to be in quadrant 4, let's do 14 first. Quadrant 4, then I need to do 2 pi minus that angle, because that's how shy I am, how much shorter of the angle I'm going to be. So I'm going to add 2 pi to that angle that I got. So let's do plus 2 pi. So for quadrant 4, we get an angle, that is about 5.84. I'm going to round 6. It's 84668, so I'm going to round that up to 7. Okay, so that's our answer for quadrant 4. So let's think of quadrant 3. Remember, this is sort of the time, that's the horizontal gap, that gap right there. So our gap here is 0.436. I'll use the positive. Right? If I think of this as a triangle, that's the angle inside that triangle. So for this quadrant, my theta is going to be pi, since this is pi, well, above it, so minus 0.436 instead of 2 pi. So let's write that down. So theta is pi minus 0.436. So I take that original number and I add pi to it. Which gives me 2.7052. So I'm going to keep it at 705. Okay, and just like the last one, we're going to, sorry, I moved my screen here. Just like the last couple sets of problems, it says explain why the answers to problems 13 and 14 are different, even though the calculator gives you the same answers for both problems. So we're going to talk about tangent now, and what sort of the options are for when we do inverse tangent. So now for our question, like we said, we were in quadrants 2 and 4, because that's where tan is negative, right? So positive tangent, negative tangent, positive tangent, and negative tangent. So just like before, our calculator wants to give us the closest answer to 0. So here's where positive tangent is. So when we do tan inverse of some positive number, our calculator will give us a positive angle in quadrant 1. I'll write out the word quadrant. In quadrant 1. The closest negative value to tan is down here in quadrant 4. So if we do tan inverse of some negative value, it's going to give us, again, it wants it close to 0, so a negative angle in quadrant 4. So those are the two things that get, well, negative angle in quadrant 4, that's going to be just like before. If we're counting clockwise, we're going to use negative pi over 2, right? So we're going clockwise here. So negative pi over 2 will be the smallest possible value before that crosses over to be a positive tangent. And positive pi over 2, right, that's counting counterclockwise. So it counts in two different directions. So positive pi over 2 is their biggest value. So that will always be our answer for tangent. So this once again relies on us understanding that our calculator won't give us an answer, won't give us an angle in quadrants 2 or quadrants 3. It doesn't need to, because if it's positive, it'll just give us something in quadrant 1. And if it's negative, it'll just give us something in quadrant 4. It'll use the negative version of that angle, right? Negative angle, so closest to 0. Zero possible. Okay. Question 16. And it just has sine of theta equals -1. It doesn't give us any other connotation, right? So let's draw where we have a y value of -1. And not only a y value, but also we can think of sine of theta as y over our radius. So if I were to draw a circle, and it doesn't have to be a circle, but I'm going to show this problem with the circle. We'll pretend that has 0, 0 as the center. That means if my r, let's say a radius of 1, if I'm down, I have a y value of 1 with a radius 1. Well, there's only one spot that we get that exact answer, so that's why it doesn't need to give us anything else. Our answer is 3 pi over 2, because it wants it between 0 and 2 pi. So I don't even need to pull my calculator out for this. 3 pi over 2. If you do want to do the decimal approximation, because it says 3 decimal places, we can throw that in here. 7, 1, 2, 3. So I'm going to keep it at 2. So decimal approximation. But I'm always a fan of using exact values when you can. So question 7, explain why problem 16 only needed one clue to determine the unique value for theta. Well, that's kind of what we just did right here. So there's only one place between 0 and 2 pi that has a sine value of -1, right? We could, if we did sine inverse, if we had used sine inverse to do this, if we had done sine inverse of -1, our calculator would have probably given us the decimal version, right? It would have given us, well, it actually wouldn't have given us 4.712. Because remember, it always gives us the number closest to 0 possible. So if we had done sine inverse of -1, it actually would have given us -1.571, because that is, or, right, negative pi over 2. But we know negative pi over 2 and 3 pi over 2 are coterminal, meaning they have the same terminal ray. So the same terminal ray right here, right? That same terminal ray. Okay, so fill in the indicated information for each of the inverse functions. So it wants us to graph y equals sine inverse of x, and it gives us a little grid underneath. So I actually think it'll be helpful to do the domain and range first, right? So let's see, it wants us to, so graph y equals sine inverse of x. So before we graph the inverse of x, let's think of just like in general, sine of theta, right? So sine of theta falls between 1 and -1, right? If we think of our graph, our original sort of graph of sine of theta. So let's sketch y equals sine of theta. Y equals sine of theta. So that starts at the midline. We go up to 1, come back down at 0, go down to -1, and we come back to 0. That's just one period of sine of theta. So 0, pi, and 2 pi, right? So that's a sketch of it. So first of all, if we think of what can I do if I take the inverse of all these to get the theta by itself. So then I do the inverse of everything. Sine. So notice theta is between sine inverse of 1 and sine inverse of -1. Well, we have that as where our x value is, right? So our x values must be between -1 and 1. So that's our domain, -1 to 1. So we're going to have this on a pretty restricted domain. Okay, so if that's what we get out, remember when we did sine inverse, we already said that for sine inverse, that theta, the highest value of theta we get is pi over 2, and the lowest value of theta we get is negative pi over 2, right? We explained that that's where it's a positive sign and a negative sign. Negative sign, right? Negative pi over 2 and pi over 2. It's going to give us an answer in quadrants 1 or 4, right? Quad 1, quad 4. So it's always going to give us an answer between those. So our range is negative pi over 2 to positive pi over 2. So let's plot those, right? When sine, so if I have an x value of -1, right? If I have sine inverse of -1, I get an angle of negative pi over 2. So -1, well, here's negative pi, so negative pi over 2 is going to be right here. So -1, negative pi over 2. Okay, and then x is 1, right? Sine inverse of 1. That gives me an output of positive pi over 2. So right there, pi over 2. So what's happening when x is 0? Well, sine inverse of 0 gives us 0, right? Where's the y value? 0. Well, it's at 0. So it gives us 0, 0 here. Now we could keep filling these in, but we can also use our sort of knowledge of the sine graph to understand that we're going to curve, and to get an even better image, I'm going to sketch a little bit more of this graph. I'm going to go down here and back up there. So here, right, that's where we're seeing this negative pi over 2, -1, but notice we use the inverse. And here, this is where we're seeing the positive pi over 2, 1. And there's our 0, 0. So notice we're curving upward on this segment here. Let me highlight it, right? So that means we're going to have, it's an inverse curve there. It's going to curve the opposite way. And here, when we're curving this direction, so that's going to create our curve. And I hope you excuse my language there too, because it's curving upward. Now, I didn't describe those very perfectly, but hopefully we can see that we are reflecting it over y equals x there. So there is our graph for y equals sine inverse of x. So now we're going to do the same thing with cosine. So graph y equals cosine of x. So let's kind of break this down the same way. Oops, cosine of x. Cosine inverse of x. Right, so cosine of theta was always between, just like sine, -1 and 1. So again, cosine inverse for each one, -1 and cosine inverse of 1. So our domain, and I'll even put x I don't need to put theta. We're using x here, so I can do x. So our x values, actually I'll keep it theta so that we can, because where we're putting x is right here. Let's highlight a little. So our x value is between -1 and 1, just like before. So that creates our domain, -1 to 1. Okay, so, and let's actually sketch, again, I like that we sketched our function out before, so let's do that again. Let's sketch it in blue. Let's sketch y equals cosine of x here. So we start at the maximum, we come down, down again. So there's one period. I'll do a half a period this way as well. Okay, so here we have the point 0, 1. Here we have the point pi over 2, 0. Here we're pi -1. And here we're 3 pi over 2, 0. Let me fix my parenthesis there. And here we're at 2 pi 0. I don't need to label the left side. Because we also said, remember we said cosine is positive in quadrants 1, and cosine is negative in quadrants 2. So when we do cosine inverse, right, we said the highest value we're going to get is right here, because this will give us all the negative cosine inverse values, and the lowest one is 0. That'll give us the positive one. So our range here is now 0 to pi. And because that's going to give us the positive and negative versions of cosine. So let's take that range 0. Notice there are positive cosines here and negative cosines there, right? Negative and positive. So we can really see where that range is stemming from. Where on this one, we had positives and negatives. Okay, so 0, 1 becomes 1, 0. Okay, and pi -1 becomes -1 pi. Now notice we had pi over 2, 0, so that's going to become 0, 0 pi over 2. So those are sort of our max, midline, and min points that we're focusing on. So now let's think about how this should curve. Since we are reflecting it over y equals x, since it's curving, we're seeing it looking concave down there. That means we want to make it look concave up. We want to curve the opposite direction. And when cosine is negative, we see it looks concave up, so we want to curve it to look concave down, the opposite. Let me make that a little better. So we want to curve it in the opposite direction. And there we have cosine inverse of x graph. Okay, let's graph y equals tan inverse of x. So let's rewrite that over down here. Y equals tan inverse of x. So let's think about the domain and range first. Well, let's graph just like before. When we think of domain and range, it might be better to do a graph we're a little bit more familiar with. So hopefully we're a little more familiar with y equals tangent of x. So let's think of that. Remember, tan, and another way to think of tan is sine of x over cosine of x. So basically, right, when sine of x equals 0, so does tan of x. So when sine of x equals 0, so does tan of x. So remember, sine of x is 0 at 0, 0. Then we go up pi over 2. We're back at 0 at pi. So pi 0, 2 pi. Every full circle, or actually really every half of a circle, sine is 0. So negative pi 0. So let's all do. And let's think of it this way. When cosine of x equals 0, tan of x is undefined, creating a vertical asymptote. And that's because cosine of x is in the bottom of our fraction, so we can't have 0 in the bottom of our fraction. It creates that vertical asymptote. So let's do that in this pink color, I guess. So cosine of x is 0 at pi over 2. So about halfway. So x equals pi over 2. And 3 pi over 2. X equals 3 pi over 2. And negative pi over 2, and so on. So every, that should be negative pi over 2. Negative pi over 2. So we can see that every pi, there's a new vertical asymptote starting at pi over 2. Now, that's not my most perfect graph, but that's pretty good. So now if we think of how this curves, and I like to do pi over 4, thinking of tangent of pi over 4, because tangent of pi over 4 is 1. So if I have a pi over 4, I'm going to have 1. And tan, if I have negative pi over 4, I'm going to be down at negative 1. So it creates this kind of curve that looks like this. And now every time we have a vertical asymptote, it kind of breaks our graph up into pieces. So this is our graph of tan of x, a very poorly sketched graph of tan of x, but we can see the domain of this graph. It repeats itself. So our domain, or actually before we even get to domain and range, right? Let's think when this graph starts repeating itself. Well, our range, let's start with range, because that's going to be the domain of the inverse. We actually can keep going up. There's only, we don't have the restrictions like sine and cosine. So we have all real numbers, or negative infinity to infinity. So this becomes, so remember the range of this function, this is the domain of the inverse. So domain of the inverse. So we can go ahead and put our domain as negative infinity to infinity. We didn't have to and do it that way. There's a few different ways we could have found that domain, but there we go. We could also have thought of this the same way as we did for the other graphs. Now let's talk about range. So the range of this function, well, that's going to be what's equivalent to our domain. So we see that we have this negative pi over 2 and pi over 2. Those are their closest vertical asymptotes to 0. And those points actually create vertical asymptotes, so I can't include them. So I'm going to say negative pi over 2 to pi over 2. Because when I do my inverse, so the inverse will always give me, so inverse will give me something in this interval. We'll give an answer. We'll give an answer in this interval, in this one right here. So domain, we're going to use, the domain of tan of x is the range of tan inverse. So negative pi over 2 to pi over 2. The period is pi. It repeats itself every pi. So that's a little note. The period of tan of x is pi. So let's use that segment right there let's use this segment to graph. So there's my negative tan values. And let's look at my positive tan values. So my negative tan values and my positive tan values, let's take a look at those. Well, the vertical asymptotes are going to become horizontal asymptotes. So I'm going to have a horizontal asymptote at horizontal asymptote at pi over 2 and negative pi over 2. So horizontal asymptotes, y equals pi over 2 and y equals negative pi over 2, right? And we're seeing that in the range that we can't touch those. We're not including those values. But our domain is going to be all real numbers, so we're going to take up this whole space. So let's look at our 0, 0 point. That doesn't change when we have an inverse. It does not change when we have an inverse. So notice on our positive, when tangent is positive, our graph over here looks like it's concave up. Concave up, it's curving upward, it's bending. So when we put that on our graph, we're going to be concave down. Now you can also think of starting at 0 and approaching that asymptote. Okay, and when tangent is negative, it is concave down. So we're going to bend the opposite way. We're going to bend to be concave up, or think of it as approaching the asymptote. So there's our graph of y equals tan inverse of x. It looks like the regular tangent graph flipped on its side. Okay. Well, I should say flipped on its side and then curved different directions. But anyways, let's move on to our next problem. I'm just going to move the screen. Okay. Question 21 says plot the given point with r and theta in the polar coordinate system. So r is 5 and our angle, what's happening here, my computer is jumping all over the place, is 2 pi over 3. Sorry, my screen keeps jumping on me. So this is how many sort of spokes outward we're going to count. So kind of think of that as like the spokes that outward. And this is sort of where we're going to go. So if we say that this is 0 radians, I don't know why I put degrees, 0 radians. This is pi over 2 radians. So this looks like it's probably pi over 6, and this looks like it's probably pi over 3. So here is 2 pi over 3, I'd say. So let's count out 1, 2, 3, 4, 5. Let me double check that that's 5, right? 1, 2, 3, 4, 5. So there we go. 5 pi, and then 2 pi over 3. Okay, so 3, 7 pi over 6. I'm going to rewrite that. 3, 7 pi over 6. So, right, okay. So 7 pi over 6, well, here's pi. So 7 pi over 6 is right here, right? Remember, the pi over 6 is the same as third degree angle, so those are always going to be closer to the horizontal axis. And 1, 2, 3. So 3 pi, 7 pi. Question 23. So 5 pi over 3, right? So here is, I'm going to write this as 6 pi over 3, right? Or, so right, 2 pi. So 5 pi over 3 is going to be down here. 5 pi over 3. And we're counting out 8 spokes. So 1, 2, 3, 4, 5, 6, 7. There's our 8th spoke. Okay. So we have 9 and then pi over 3. So 9 pi over 3. So pi over 3 is right here. So 9. So 1, 2, 3, 4, 5, 6, 7, 8. We're all the way at the end there. 9. Question 25. So 5 pi over 6, that's, remember, pi, or 6 pi over 6 is right here. So 5 pi over 6 is going to be this spoke right there. And we're counting out 7. So 1, 2, 3, 4, 5, 6, 7. There we go. Trying to make this a big dot, and it keeps auto-correcting. All right, so 7, 5 pi over 6. Okay, negative 6 and pi over 3. Our graph is all the way down here. Negative 6. And was it pi over 3? Let me just double check. Yep, positive pi over 3. So let's find where positive pi over 3 is. That would be right here. Pi over 3. So negative 6, we're just going to count away from pi over 3. So I'm going to highlight this line a little bit darker. Right. There we go. So negative, let's go back to my pink. So we're starting at, I'm going to undo. I moved my screen a little bit. And I did it again, so give me 1 second to adjust that. My apologies. Okay, so 1, 2, 3, 4, 5, 6 in the opposite direction. We're not going towards pi over 3, we're going away from pi over 3. And I keep moving the screen. And I think that was our last question. Yeah, so there's the last question on Unit 7, Lesson 8, Ready, Set, Go. I hope you found this video helpful. Thank you for watching.